some of the fundamental ideas where statistics has a tremendous implications in dealing with the several concepts in machine learning. As last lecture, I have pointed out that there are many blogs and many and there, you know that there are many people, lot of people are now doing machine learning, and some people even there is a wonderful document that 50 years of data science written by one of the Harvard statisticians. Uh, he uh, he said that, and there are a lot of viewpoints of various different scientists from different domains, and there is names of certain blogs he has put where he has mentioned that, well, for doing data science you don't need even statistics. So you see that there are a lot of things are happening. So given the statistical machine learning with us, there are some of the ideas which are very important. So and and the foundations of those actually lying in the statistical theories. So I think these are some of the things which you have already seen in your other earlier lectures. So, for example, handwritten digit recognition data. This is one of the very popular data sets, and I think first-hand practice uh, people do for applying some machine learning use this data. So most of the time, what we realize that rather than be trained in machine learning ideas, there are ready-made codes for that is available in Python or R in the internet. People usually copy it and run that and publish it in different social media platforms. That I have done some kind of machine learning. So, however, many of the ideas are very concrete ideas. However, it's just running the Python code. It ends up. So this is something. So we have seen that we have learned about two problems. One is the regression problem. One is the classification problem. These are the two things you have learned. So let me take into a concrete thing. So in your previous lecture, this slide is important. So in our previous lecture, we have seen that multiple linear regression, which you have learned already. That there you usually have an input variable, you have an input, and you have one response, and you have prediction equations you find of this form. And how did you get this prediction equation? You write down this residual sum of squares. This is the form that I have written in our previous lectures, and you minimize this with respect to beta, and you you get the estimates of beta hat. So in general, if we just a two-dimension scenario, if we just look at it, this is something they estimate what is beta naught, and then the slope along the x direction. So basically, partial derivative of this plane along x1, basically this slope is beta 1 cap, and direction along this x2 is basically beta 2 cap. So basically, for a two-dimensional case, you get a plane. The same thing if you are having in a one-dimensional scenario, you have only one predictors and one, then you get a line fitting. That's we have learned already. Now, as you understand that if as we go move into higher dimension, so you are going to, if you are having a p many predictors, then basically you get a p dimensional hyperplane, right? Yes or no? This is a p dimensional hyperplane you are going to get. And based on that, so you can understand that this is your observed data, its prediction basically this one, that where on the plane. Similarly, this is the data, its prediction basically it is this. So this plane which basically represents your y hat, which is the prediction equation, right? So what is the same thing many people try to apply it in the case of classification also. So if you have a label data, basically if you have two predictors and each of the row contains some different classes, and if you apply the same idea, that which is the least square fitting, then you get a prediction equation of this form. So as you see that this is the line that you are observing over here. So anything falling above this is going to be classified as this. Anything falling below, it is going to be classified as this. So least square method, we have understood least square method can be applied to a regression problem also, to a classification problem also. But when you're applying in a classification problem, you have to be very, very careful about it, that how you are applying it. Because in general, most of the exercises or most of the examples you'll find in the internet, typically least square methods does not is not being applied to classification problem. However, it is possible to do, because in fact here also in this workshop you have learned the classification problem by using logistic regression method. Okay, so let me skip this part. So this document will be there with you. So how this some of the codes, how these pictures being generated, those things have come up. Another idea that you have learned it, that nearest neighbor regressions. This is one of the very, very popular method. It says basically that when you are observing, when you have a data values, so it says that whenever we are performing a regression task, what we are doing, we consider a global linear or global function, right? We assuming that there is a curve which is represents the population relationship. However, we may come into more and more flexible methods in a sense that, so if I want to predict some values at this input, then its nearby values probably is a better representation of this. It could be, yes, makes sense. If some values over here, so this is not going to have much impact on this, but whereas the nearby regions are going to have a more impact on these values. So which has come into a called what we call the nearest neighbor methods, right? Now this concept is very important in the context of machine learning. Let's say for example somebody considers that I'm going to consider only one nearest neighbor. So if I consider one nearest neighbor, this is the wonderful graph, wonderful fitting you see. So this value is being predicted with the same value. So here, if I take the predicted value minus that observed value, they are actually zero. So that means if you calculate the sum of square error, this is actually zero. So there is no error here at all. So can anybody tell me what is this scenario typically we tell in machine learning? And anybody can put a message also. So we end up with a very wonderful perfect fitting, right? So we have got hold of a model which gives a which contains no error at all. Anyone? Okay, okay. No, no issue, no issue. So this is the scenario typically what refers to as a overfitting, that you got very, very close to the actual data. So what is going to be the impact of this? Because of this, your some data you have already learned what is called as a test data. When you build some model, you put some data aside for testing, so its performance going to be very, very bad on the test data. So when we have a model which perform tremendously well in training set and post performance in your test data, it is the scenario which is typically called as overfitting, and we must avoid it. So this is a very, very important concept that we must, because many times we have very small data sets and we fit a very highly complex models, and we saw that the it's almost got all the points. However, rarely there is some validation people consider, so which we should always avoid. So these things I am not going to talk about. So this slide will be there with you. So this will talk about how model flexibility and how model complexity, basically these things is important. So where I want to focus is over here, that a kind of a probabilistic framework is before getting into the our current topic. So we want to understand, say for example, you have y, your response, and you have your input. So this is we call it as a response, and this is we call it as a features, right? So it is basically usually multi-dimensional. So it can have a p-dimensional features, right? Correct. And you have the, this is a response, and we want to find, so basically the whole goal of machine learning is that we seek a function f which models the relationship between y and x, so that the distance between this y vector and this fx, so this is, note that this is an expectation, and the expectation means it is an averaging. So we seek to find a function f, or relating to a function f, that when we pass this input with f, the expected error, so y minus fx, this is going to be minimum. So this is what we call it as a expected prediction error, EPEF. So which is nothing, expected value of y minus fx whole square, and which is nothing, if we write it in mathematically, this is represent the joint probability distribution. So we have to take the integration with respect to the joint probability distribution of dx and dy. So we want a choice of fx that minimizes the expected prediction error. Now this form of fx you may thought of can be a linear regression, right? You may thought of a k nearest neighbor regression. You may thought of a polynomial regression. You may thought of a piecewise linear regression. You may thought of a spline regression. You may thought of some other nonlinear function. So you have to choose some a for which this expected prediction error is minimum. So that choice of if we need to choose. The whole, almost the whole regression problem is basically in machine learning can be summarized by using this single equation. What we call it is a expected prediction error. Now, if that is the purpose. You see, there is a prediction error. That means we want to choose an f which is going to give me less error if I am predicting the future. But who has seen the future? Nobody has seen the future, right? And that is the purpose, that when you get a data set, you take certain portion as a train, and using this you train this f, and then you, how good it is performing on some unseen data that you perform. But finally, this test error, that on a test performance, when you calculate this, basically an estimator of expected prediction error. Those who had are from statistics background, you have learned about the risk function. What is risk function? If you have an estimator t and expected value of loss function t with respect to the parameters, and L is the loss function that you know, and expectation of the loss function that is usually defined as risk function. So this is nothing in the machine learning literature. This is the risk function what you have learned for the parameter estimation scenario. Here also it is the absolutely same idea. So please keep this in mind. If you have, because risk function is also has a decomposition. If you consider the squared error risk function, it also has a decomposition, that variance and bias. Because any function, any estimator, you have learned that you can. So basically, if you have a MAC, mean squared error of t, this you can decompose into variance component and bias of t, its squared component. And if you have an unbiased estimator, you basically get MAC is equal to variance, right? So here the whole machine learning idea boils down to this particular statistical concept. Please understand it. Many of you come from a statistics background. We learned that in our UG or PG level, but when we see this quantity in machine learning, we thought that something is very different we are learning. It is absolute. It is the same and same and same idea. So this is the prediction error. So which is nothing. If you look at it, it is nothing but the mean squared error. So here for the statistics or math bio people, so you revise little bit of the risk function from your background and try to connect this, because this is one of the most fundamental equation in machine learning. So when we try to minimize the expected prediction error, so typically we condition on X. So what is this results? We know that expected value of Y, then we give an expected value of Y. This turns out to be expected value of Y. This is the relationship we know. Or I think this is called as a something as a covering principle. One of the very fundamental results from statistics or the probability, whatever you say. So as you observed it here, there are both X and Y to be considered as random quantity, right? And this is the expectation. So here, if I condition on X and I take one more expectation, I'm going to get the same thing, the left hand side. That's precisely what is being done. So what we did, conditioning on X, then again this evaluation has been done. So finally we get the same expected value. As you observe that here, now X is conditioning. So X is condition. Note it very carefully. This is X is condition, and suppose that your fx is equal to a plus bx. Suppose, just assume. So in that case, expected value of y given x, y minus a minus bx, this whole square, it is nothing. It is going to be y minus a minus bxi whole square. So I is equal to 1 to n. Right? So maybe possibly something 1 by n. So as you observe that this is the part in real life, in all applications, most of the applications I would say, that we consider your y, if the data is something like this y, x1, x2, xp, this is the data we get y1, x11, x21, like this x1p, like this yn, xn1, xn2, and xnp. This is the Excel file we get usually as a data, right? And we minimize this thing. So basically, almost in all the applications, we work with this condition. We do not consider this, and we assume that it is our assumption that X basically is a fixed, that inputs are always fixed. So basically, we work on this conditional averaging of the sum of squares, right? And those who come from a little bit of statistics background, you know that you know this, right? That if I take a random variable and if I want to minimize this quantity with respect to C, then the choice of C is coming as expectation of X. So we always say that expectation formula is E of X, means it is integral of X fx dx. But expectation has one more interpretation also, that what is that particular point from which the random variable maintains a minimum squared distance. So that is minimization of C, expected value of x minus C whole square, for which C, this quantity is minimum. The solution is turning out to be expected value of x. So in principle, if you are talking about this minimizing the sum of squares, or maybe finding out a function f for which you have the minimum square deviation from your response, so basically you are looking for a function f which is nothing but expected value of y given x is equal to x. And that is precisely in machine learning literature called as a regression function. This is not something coming from a like something very very new idea. However, this is something we already knew. This is a problem which usually to deal with our UG level. So that means the function that you are looking for, which is nothing but expectation of y given x is equal to x. That's it. So that means when you are basically trying to make an average of y when x equal to x is given. So those who have written from a stat background, they know that typically sometime we write down the regression equation also as this: alpha plus beta x in the conditional way, right? Some of the book prefer to say like this. The idea is that given x, this is the distribution of this. So the idea is that the solution that you are looking for, it is nothing but the conditional expectation of y given x. This is the idea of regression. Now what we consider, we consider various different forms of the this regression function and try to estimate it. And that's it. That's what I wanted to discuss with you. So now this slide will be there with you. So how to calculate that average, what is the role of nearest neighbor, those many of these methods are intuitive, very extremely and wonderfully intuitive. Like you don't have to worry much of that thing. Once I understand that concept, rest with the machine learning ideas it will follow automatically. Right? So these are something which we already have seen in your previous lectures. Just to tell you final of this discussion, that we we know that the definition of, say, if you have a random variable with distribution fx, we know that the median is something that minus infinity to c or m fx dx is equal to half. And the same is, I'm writing in a continuous random variable I'm writing. So this is basically true, right? If we have a median of it. So basically there is that point below which we have half random, half point. But median has another interpretation also, that if you minimize the absolute distance, expected absolute distance, then its solution, then the choice of C is turned out to be that median of X. So if I minimize the squared deviations, then the value of C we get is the expectation. But if we take a absolute distance, in that case, we sum as a median. So remember, when you are using certain Python codes or R or some other or MATLAB, if some package that you are using, then you have always observed that there is a choice of the risk function or the loss function is given. That you have to utilize the, what is the loss function, entropy loss. There are multiple different types of loss function. So whenever you are applying any machine learning methods, you must ensure to specify that also, this is the loss function under this particular loss, this is the method that has performed best. However, if you choose change the loss function, and in that case your results are also going to change, you may have some other function which is going to give you the better result. These things has to be kept in mind. So extremely important, I'm writing it, that extremely important, that what is the loss function or expected loss, which we call it as a risk function. Why this is so much important, and it must be mentioned there. So if you just want to get a uh, small statistical ideas, if you want to uh, understand it, there is one chapter, I think this is called as a you can read this risk function part from the theory of statistics. I think most of the people know about this book. Well, since we came from a mathematics background, I did not know earlier, but later got to know it. Mood, Greville, and I think Boyce. So this is a very very wonderful book written in 1973, but I found it wonderful book for understanding many of the ideas. So when this particular chapter we read, then immediately we started understanding many of the concepts from machine learning. So there is a wonderful treatments of risk function and some of the Bayesian ideas has been explained there very wonderfully. Okay, so this is I'm not getting into this that when we have a categorical or you have a prediction or classification problem, then you have a what kind of loss function that you are talking about. So they are also in the same thing. So typically, I think till now we have discussed in your this workshop in a supervised setup. So supervised learning, that when you have an training observations and there is a response. So you can perform the training of the model and you can check with the response that how much close uh, it is. So basically, it is said that the learning algorithm has the property that it can modify its input-output relationship effect in response to differences that yi minus this between the original and generated outputs. This process is also known as learning by example. So basically, you have there is a y, there is a response which is going to guide you. That you build a model and see that how much close that you are getting with the actual data, so that you can modify your that relationship. Okay? So this is in case of non-linear relationship. This is what it is. So as you see that when we have yesterday have discussed about non-linear regression, right? So there the surfaces are going to be something like this. We are basically talking about a surface and we are trying to find out the minimum of that surface. Right? So this we learned already how to do it in R, and we have seen examples also. Right? So this also I have explained yesterday that what is the role of maximum value estimation. So this is a yesterday I have discussed that if you are in a normal distribution setup, then both MLE and least square estimates these guys are similar. So for us today's lecture, this part is very very important. That if you are having in a setting that you have x1, x2, and xp, p many predictors, and y is your response, then basically you minimize yi minus beta 0 minus beta j xij whole square, j is equal to 1 to p.
Excuse me, sir.
Yes, please.
Sir, I do have a question here.
Yes,
Uh,
please.
sir, sir, I'm working on a distribution fitting. When we fit distribution or some model on a particular data set or a generated data set.
Mhm.
So, in our software, it uses MLE as default
Okay.
for estimation. My question is, there are many more methods like a method of moments estimation and LSC also. According to your opinion, which estimation method is more robust or more better to apply for estimation? What method should we prefer?
Okay, okay. So here, for example, as far as my understanding goes, because maximum likelihood estimation method has several wonderful asymptotic properties. For example, unbiasedness. Although we know that many MLAs are not unbiased. For example, the simple example that we know that if we have a sample from a normal distribution, the sample MLE of MLE what we get for the estimator of sigma squared is not unbiased. So, however, one interesting property is that it is asymptotically unbiased. So that is sure. In addition to that, you have an asymptotically, it is a normal distribution, and not only that, that you have what you have asked, you have an idea of the minimum variance attained by any unbiased estimator, right? So you which you know that which we get it from the Fisher information. So the best part of the asymptotically it also attains actually the minimum variance. That is a wonderful property of MLE. So when you are in a parameter estimation setting, MLE is definitely preferred. And method of movements, we know that method of movements is, it's not really unique, right? Because we may end up with a lot of estimators for method of movements. So like typically we use maximum likelihood estimate only because there are a lot of theoretical support is already there for it. And machine learning domain also, likelihood estimation is the most used one. But I have a separate uh, observation based on your question, because when you are saying the distribution fitting, so I am just as you my answer is just based on that, that you are basically you have a population distribution that you have fixed it and you have a sample on that, and you try to approximate the parameters. So it is basically falls into the estimation of parameters. But when we get into a distribution fitting, that what kind of, say for example, curve estimation, or when we are trying to estimate, say for example, CDF of a distribution, so then we have a different sets of, we have different sets of methods, right? Because they are you are basically approximating a full function, right? So you have a complete function itself, and using a some sample, you try to approximate the whole function. So there the notions of distance and everything is going to change there. Okay, for example, one typical example, say for example, you can density estimation. For example, if you suppose that you have a density estimation you want to go, so then you have an histogram estimator also, you have kernel density estimators also, and for each of them you can compute the risk also. So now there are the risk measure that you are going to take. This uh, may not be of this form. So it may have a different form. It may have a other distance. It may have a other divergence measure like KL divergence or Bhattacharya's distance. There are several different measures comes into play. But in your parameter estimation setup, definitely till now what application we have done, we preferred to be maximum likelihood estimate only. I hope that answers
Okay, sir.
your query.
Okay, sir. Thank you so much, sir.
Yes, yes. But yes, I think this added up one interesting idea. So to one thing you can see that there are if you, I'm not sure whether you have read this book, Wasserman, which is all of statistics. They have one very wonderful chapter, curve estimation, and another chapter they have a very wonderful applications on wavelets, and another chapter I think they have a density estimation. So I have made some interesting documents which first hand implementation, not by using packages, that how this estimation works and how to calculate the risk. So later you can drop me an email, like I would be happy to share those materials which I teach for the data science and machine learning program in our institute. Okay, thanks. Thank you. These are very wonderful questions. Okay, so should we go? Any other questions? So let me check out. Kindly share the materials if possible. Mannath, yes, yes, definitely. Here, here, writing the materials, everything will be shared. So no issue at all. But if something, some more particular topic that you have some interest, so please drop an email to me. If I don't have when I if I get interested, I will definitely write something. Because what we are observing that many of the things nowadays is becoming like, when you say that they come that with 1 month data science, 1 month machine learning, they become an expert. So we then when we investigate, or rather than we discuss small, do a small discussion, and we find that okay, so that means there is some copied code in the internet. And when if you just open up Kaggle, you will find thousands of people have already worked on that. You copy that code, run in your own PC, and get the results, and we feel that we have learned machine learning. In principle, it is not the case. So as I explained one case study, that any of those things did not actually help us in solving that case study. So real problem is always challenging, and the challenges will come. So we have to be ready for that. So when there is a challenge, so for that, foundationally, some of the ideas that needs to be clear to us. Okay, thank you very much. I think next is this. Yes. So this all you already know. So this you already know. So I'm not going to talk about it. This is one of the very very fundamental relationship in machine learning. So this is basically the decomposition that you have your future values, you have your predicted values. This is being decomposed into variance component associated with the approximator, and there is a bias component, and this is something which called as a irreducible error. So as I discussed yesterday that the population, when you say that population regression line, it itself has a variance, right? So there is a sigma square sitting. So population is not that you have a single straight line relationship. All data points are going to like this. So the population itself has a variance. So when in our estimation procedure, when our when our training MSC or training set, the error in the training set, when that training set falls below, in fact, the population level error, the irreducible error, that precisely tell, tells you what is meant by overfitting. So as you see that this has certain variance, this has certain so sigma square variance of epsilon. So when your training error, right? So you can talk when your training error is actually less than sigma square, then this is the scenario we say it is the overfitting. And lot of case studies where when we see when we give the students, because this is a common practice when you see the many engineering students, they do something from here and there and they show it, but we explain it to them that no, this is what you have done, this is wrong. Your software has given it to you, but it is wrong. Okay, so this is not something I'm going to discuss over here. So this part is very important. Now you see that this is as you see that this is a data which has been given, right? And this is the curve, the black curve that you see. This is the expected curve, and we added, and a random variation is that random noise is being added, and this data has been simulated. Now various different order polynomials has been fitted to this data, and their mean squared error has been calculated. As simple as that. And this line is the training error, and this line is the test error, right? So this graph, the original population graph, has a moderate non-linearity. Now as you observe that, so that means, as see that this is the polynomial, if you see that this is a very high degree polynomial, right? And whereas this polynomial is a low degree polynomial, and whereas this is a straight line. So as you observe that, so we are performing a some data point we are keeping as a training, some data point is testing. So we are calculating training error and test error. As you observe that number of terms in the polynomial is increasing, eventually mean squared error actually decreases, and mean squared error in fact is goes to zero. Because if you can have a polynomial actually which goes from all the graphs, all the points, right? So in that case, the training error is actually zero. So training error is always, this is a very, very important point. The training error is always a monotone decreasing function as a function of model flexibility. So more model, in other words, you can also say it is a complexity. So that means more and more terms being added, your training error eventually goes to zero. You have learned about something similar to this in a regression concept. More and more predictors you add up, the R square actually always increases. So in your multiple linear regression, that MLR, what you have learned day before yesterday, there you have seen that there are two measures you have learned. One is R square, one is adjusted R square. And you have seen that R square always increases as number of predictors increases. However, adjusted R square, eventually if unnecessarily predictors got added, then adjusted R square then decreases. So that is why when we are dealing with a large number of predictors, an adjusted R square is being preferred more, because adjusted R square saves you in keeping unnecessarily predictors in the model. So let the model be unnecessarily complex, not required. So this is something, it is the training error is always decreasing, whereas test error first decreases then increases. This is a new shape. Note that this is an universal shape. This is an universal property, this U shape. And this depends on what is the non-linearity in the population itself you are having. This simulation, this is the being copied from the book. So please don't worry, because usually I don't prefer it. So I think I have a, this is the website. The slide will be shared with you. Here, these are the codes which has been written by us, and these shapes are being generated by the written code by ourselves itself. So all those codes are exclusively written by us only. These are the figures which are generated from our programs. Okay, so you go to this website and click on this link, and you will be it will take you to how this graphs are being generated. Okay, so here you have a moderate nonlinearity, and you have a linearity, and here you have a highly nonlinear. So what is the behavior of training and test error as a function of degree of the flexibility? You will be finding it. Okay, so here you will be able to find it. Rest is, I think this is fine. So I found it. So for a reference book, extraordinary book, this is kind of a, like, for industry, for academia, for all of them. This version 2 is now available 2021. There they have added Python codes and some chapters on deep learning also. Many of people already probably reading this book, but please, if possible, read it as a storybook only, because this is being written for non-technical audience. But however, many ideas are exceptionally very wonderfully explained. This is the book. So I think it first appeared in 2011. So 2021 edition, which they have included some of the, like, neural networks and other things they have added. In earlier version, it was not there. If somebody is interested more math part of this, they can read this book, Elements of Statistical Learning. This is a, this is pretty maths on pretty mathematical book. So many of the ideas are actually taken from here. So you can consider that this is a lighter version of this particular book. And if you're dealing with R, because this program using R, so some hands-on machine learning with R, this is also, I found it, this book pretty nice. So I'm only showing those books which I have read. So some other people have said that is good, that is good. I'm not showing it here. So these three books I have read, and I have seen it, or they have worked on it. I found these things to be nicely followed. So this is must for all. This one is if you are from a maths and stat, a bit more interested in theoretical understanding of that. This is also for all. So this will give you practical applications of machine learning using R. These are some of the websites that I keep on updating over the time. Whenever I read something interesting, update it there. So if you're interested, you can have a look at that. So this is the idea which I wanted to give you all about the some of the basic and foundational understanding of machine learning. Now let me share my screen once again. So by now we have understood basically what is the risk, that where what are the experiments we are doing, what basically we are doing if we are in a regression setup. I'll put more emphasis on regression only. So we basically are minimizing yi xip whole square. This is the quantity what we are actually minimizing. Now, if you take your data centered and scaled and do all these things, then in that case, you can actually write it down in this fashion also, that yi minus beta xi1. So you basically get this absorbed into y1, and you and beta 2 xi2 minus beta p xip whole square. So if I just consider it to be in a two-dimension scenario, so only in two-dimension scenario, so this turns out to be yi minus beta 1 xi1 minus beta 2 xi2 whole square, right? So this is actually a function of, rather than I'm writing g of beta 1 and beta 2. This is a function of beta 1, beta 2. With little bit of effort, you can see that this function basically, if this is your beta 1 axis, this is beta 2 axis, and this is the function, actually looks something like this. So that this is the points where actually you achieve the minimum. So this is the estimate which we call it as a beta 1 and beta 2 cap, right? This is one thing. Now this is typically when we perform this minimization. So I'm right now taking a short beta j x I j. When we perform this minimization, so this minimization works very very nicely if we have n is bigger than p. So what does that mean? Means sample size is bigger than number of predictors. So in other words, your number of rows is more than the number of columns in your data, in simple words. And if your p becomes bigger than n, so that means your number of rows less, whereas number of column is more. Means number of predictors is high than number of rows. This is what is the scenario we call it as a high dimension. So that means in such a case, when you have a high dimension, it does not have a unique solution. So here the estimates from this minimization that you get, typically it looks something like this. So from after minimizing the system of equations that you are going to get, it does not have unique solution. So that means it boils down to a problem that you have too many predictors, and you want to find out which are the predictors what are important. So now you want to find which predictors are important, right? So understand, this is one problem. There is another problem. So you understand the problem, that when you have a number of features which are more than the number of, that's a problem we do not have a solution for that. So out of that we want to find out which are the predictors are important. Another problem is, in your multiple linear regression concept, it must have been explained what we call it as a multicollinearity. What is multicollinearity says that when one predictor, one feature and other feature, they have a very high correlation. So again understand, when you have there are two features which have a very high correlation, and what is going to be the impact of this? Because of that, that the prediction that you are making, it is going to have a very high variance. What is that? What is the reason for that? As simple as that. Those who are from, at least from mathematics or statistics background, you know that the estimate of, or the estimate of this x transpose x whole inverse x transpose y, and you can actually compute the covariance of beta cap. This is sigma square x transpose x whole inverse. Now this is the matrix which is actually the data matrix, or the input matrix of the, which is the input that you are giving. Now if two predictors, if two columns of this matrix X, they are going to have very high correlation, that means one can be written as a linear combination of other, like is a constant time of the others. So in that case, the determinant turns out to be very close to zero. So in that case, this matrix X transpose X is determinant is very close to zero. So what is going to happen? Because of that, the variance terms of beta 1 cap and variance of beta p cap, this will be very high, right? So because you are going to have a, so in the denominator will be very zero, because it's going to be inverse, which is going to be very close to zero. So that means the covariance or the variance of these things are going to be very large. And what will be the impact of this? Prediction error, or prediction uh, will be very wide. So in other words, I'm using this language, it is something like this. That means the statistically variance associated with your prediction is going to be very large. This is the scenario what is being called as a multicollinearity. So that means in such a scenario, you want to drop those variables which are showing a multicollinearity. What is the solution for that? What is the solution for that? So typically, I'm explaining two of the thing that how this is uh, being tackled. Say, for example, you add some impurity in input. What does that mean? That what is the solution that you are having? X transpose X whole inverse X transpose Y. And this guy, there are due to multicollinearity, this guy is ill conditioned. So this inverse, so the variance is going to be very high, right? So the inverse basically does not exist, or it is very close to zero. However, if you add some impurity, that means if I call it a new estimate, and if I add some kind of a small impurity over here, so that means this typically is considered to be small. Got it? So this typically, this impurity considered to be very small, because you are basically tampering your input. And in such a case, so you are adding some quantity, and because the matrix X transpose X plus lambda I becomes invertible. So in that case, your variance of beta cap, that's basically turns out to be X transpose X plus lambda I whole inverse sigma square. So now this variance is under control. But what happened because of this? But what happened because of this? That if you take an expected value of this, then it is going to be X transpose X plus lambda I whole inverse X transpose Y. So, and Y is equal to your X beta. Now see that now this guy is not is equal to beta. So that means beta cap R. So let me write down R. is no longer unbiased. Very, 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 very foundational idea is that what you're doing, that you have a statistical learning method, which in this case it is a regression setting. What is the problem happened, that you have multicollinearity issues in the predictors. So because of that, you are going to have a very, very high prediction, high variance associated with your estimate. You want those estimate to be as accurate as possible, and you want their standard error to be within control. However, because of this kind of dependence in your predictors, your variance is going to be extremely high. So to reduce that variance, to get the variance under control, you introduce little bit bias. So this lambda is basically that takes care of that little bit bias you are introducing. But inclusion of this little bit bias, you get a heavy control on your variance. This is one of the very, very wonderful example of bias variance trade-off in machine learning. Again, I'm repeating. The idea is that you introduce some bias, and because of that small bias, you get a heavy, heavy control on your variance in the standard error associated with your estimates. So this is one of the very, very important concept, and this is something what is called as a ridge. People call it as a ridge regression. Right, and the solutions for the ridge regression turns out to be this. Now, how is probably for us it is fine, but how it's an optimization point of view, how does it look like? So from optimization, it looks something like this. That means that you are minimizing this yi minus, let me take only two variables, beta 2 xi2 whole square I is equal to 1 to this, and you are performing a you are minimizing this quantity, some lambda of beta j square, j is equal to 1 to 2, only 2. So you are minimizing this with respect to beta 1, beta 2. So this is the quantity now you are minimizing. This is one setting. Okay. You can write it down in a constraint optimization scenario as well. How does it works? That I is equal to 1 to n yi minus beta xi1 minus beta 2 xi2 whole square. You are minimizing with respect to beta 1, beta 2, subject to a constant is there, that beta 1 square plus beta 2 square less than is equal to s. What is this? This, I think we can plot this actually. This quantity we can plot, because it is going to be a kind of a quadratic in beta 1 and beta 2, right? So if this is my beta 1 and beta 2, and this is the, suppose that I'm taking s is equal to 0.5, in that case I get a circle, right? and and there is the, you can remember that this is going to be a surface in the beta 1 and beta 2. So there is a surface, and if I take a projection of this surface on the beta 1 and beta 2, this is actually the actual minimizer, beta 1 cap, beta 2 cap. This is the actual minimizer. However, you have specified that it has to be minimum subject to this constraint. So if this is the minimum, then constraint is not satisfied. So you have to expand this contour of the surface. And this is what we have got a match with this. So this is the estimate which you may have beta 1 cap r, and this is going to be beta 2 cap r. So these are going to be the ridge estimate of this. So this is something very, very, so this is the actual solution. However, this is what is happening here. So we got now the variance associated. So it's not the exact estimate. There is a bias. However, variance of these two estimators are extremely small. This is one thing. But when we try to understand feature, means which are the features, which are the predictors to be included in your final model. You have seen the multiple linear regression. So when you get an output of that regression, you get a p-value as well, right? You get an estimate, you get a standard error, and you get a p-value also. These three things. And in the output, you have seen that which are has a p-value very small, those are to be retained inside the model. So as you understand that here, when you are trying to select which of the feature is important, here the values are getting reduced, but they are not getting exactly equal to zero. The estimates, so they still have a contribution in your output. Only thing is that their variance is now it's small. However, if this same program, if the same problem, we deal it like this, say j I is equal to 1 to n, I minus beta 1 xi1 minus beta 2 xi2 whole square, and we get a constant of this form, beta 1 plus beta 2 less than is equal to s. So that means what? That means how the constraint law looks like. You you all know what is the constraint looks like. It looks like something like this. Now if you draw the contours, right, you can cut into a corner point. So when you cut into this corner point, that essentially means that beta 1 is equal to 0. So when you cut into this corner point, beta 1 becomes exactly is equal to 0, right? So that means if you perform an optimization with respect to such constraint, some of the variables are going to be cut down. Means their coefficients are going to be exactly equal to 0. So this is something what we call as a lasso, and it is a very commonly used technique in machine learning. That lasso has a variable selection property. Lasso has variable selection property. So the lasso, the optimization in the background that is happening, it is of this form: yi minus xi1 minus beta 2 xi2 whole square plus lambda times modulus of beta 1 plus modulus of beta 2. So this is the optimization in the background which is actually happening. Very important concept in in machine learning. This is one of the most used and popular method. So this is what is called as a lasso. So in general, so as you see that if you apply lasso for p many variables and you have this multi-dimensional in a, there are a lot of, you can imagine the constraint with a center, and you have a lot of corner points, and you have this contours coming up. So the contours is going to cut many corners. So in that case, many predictors are actually going to be exactly equal to 0. So this is something what we call it as a lasso. And one thing you can observe, so you can actually generalize this idea. So this idea actually can be generalized very easily, that you can consider I is equal to 1 to n yi minus summation j is equal to 1 to p beta j xij whole square plus lambda times summation modulus of beta j to the power q. So you can have an optimization or with respect to betas, right? What does that mean? So if your q is actually less than 1, 0 less than q less than 1, in that case, how the contours will look like? How the constraint will look like this. So you see that you have a sharp corner now, non heavy non-differentiability, right? If you have q is equal to 1, this is the constraint how it looks like. And if you have say 1 less than q less than 2, so you are going to have a something like this. And if you have a q equal to 2, it is circle. So if you have q is equal to 2, this is going to have a circle, right? Similarly, if you have when q is bigger than 2. Now understand that means you have, this is the surface whose projection you are taking, and it is going to cut down these corner points. Now if you imagine that you have, say for example, you have 20,000 many features. Typically when we deal with gene expression data, we have say 60 many patients, but we have information on 24,962 genes, and we want to find out which are the genes, which are the gene expressions are most significant for the classification of this disease. Right? It's a classification. So we have the gene expression data. Who does not have this disease? Who have that disease? We have those, right? So, so you are actually dealing with an optimization problem in a 20,000 dimensions, right? So if you imagine this in 20,000 and you perform this task, lot of corner points, like you can imagine a kind of a very a sharp ball which have a lot of corner points. So when you approach that contours, lot of variables are going to be cut, right? So here cutting is going to be very large. For example, here cutting would be less. Here cutting would be more or less, because they are mono lot of, it may end up over here, it may end up over here, it may not go over there. Here cutting will be more or less. Here in fact there will be no cutting. Here in fact there will be no cutting. So this is depends on on the applications that you are dealing with. This is a generalization of the lasso, typically call it as a q lasso. Understand the motivation for it, because software will do everything for you. So this is something that what kind of features, different sets of features are going to be selected depending on the what kind of constraint you are using. Sometimes sometimes it might happen that you want to consider, so if you consider a lasso, lot of variables being gone. If you apply reach, no variable is gone. So you may want to have a some kind of a like trade-off between both of them. So you may not want to live completely on lasso. You may not want to completely live on the reach. So that means you are basically considering something like this: I is equal to 1 to n yi minus summation j is equal to 1 to p beta j and xij whole square plus lambda. This is basically the minimization. This is something which you are doing, where alpha lies between 0 and 1. So that means you want to retain some properties of reach, and you want to retain some properties from the lasso. So your constraint is going to be now a convex combination of reach and lasso. Now which one is going to want to retain more? This will depend on the value alpha. So alpha is higher, more than 5, 0.5, means you want to retain more properties from the reach. Alpha is less than half, that means you want to retain more properties for the class. So you want more variable cutting to happen. So this is something which is called as a elastic net. So that means what is mean by that feature selection? What we understand, that you are having a you are having you basically having a p dimensional, you are having you are having in many data points represented in a p-dimensional space, and you have a surface. You want a minimizer of that surface, and what you did, you consider a around that, what is called as around that circle. So if I just want to have a visualization of this in a 3 dimension, there is something like this. Here you have some circle with a lot of corners that you have. So and you have a contours over here, right? It approaches to it. So lot of variables might get cut down. So that is something, and you see that these contours are increasing, and it is going to cut wherever they are going to cut with respect to the corner points. Those variables are going to be cut down. So one is lasso, and ridge means you are going to have something like this. So there is not going to be any variable cutting down. A lasso means you are going to have something like this. So as compared to ridge, there will be more variable cutting down. If you want both of them, you want something, a properties, something from the ridge and something from the lasso. So this is another very powerful technique which is called as a elastic net. Now the main concept here comes up that question automatically comes that how to choose optimal choice of lambda and alpha. So if you are lambda, it is for both lasso and reach, and if you take both, this turns out to be for elastic net. The universal idea is same. That is an extraordinary powerful idea. This has already been covered to you. That is the very popular, very uh, like everybody likes it. Cross validation. That you do this, you perform this, find out the best set of possible values of lambda by cross validation. So the idea is very simple. You take different sets of values of lambda 2, say you take lambda 100 values. Typically, they all are close to 0. And you know how to calculate the cross validation error. So what you do, like suppose this is 5-fold cross validation. So you don't consider this, build your model based on this, and you calculate the MAC. This is called MAC 1. Then you cross this and you take rest of the things and you get MAC 2. Then you cross this and you consider this and this, so you call it as a MAC 3. Like this, you will be getting MAC 5. So here you have fixed your lambda 1. So your cross validation error at lambda 1 is going to be, so you have these values lambda 1, average of these all at MAC. So this is going to be average MAC. The same process you are going to do for lambda 2. Same process for lambda 3. You are going to get such a curve. So the values of lambda at which you have the smallest prediction error. So these are going to be, actually this is, you understand that this MAC is basically test MAC. Means which data has not been used, you are using that model to predict this observation. So this is average, I must say, test MAC, right? And this is for statisticians. This is a theory from 1983 that cross validation estimator is an unbiased estimator of expected test error. So again, it is a by statisticians. So it's not that when machine learning come and cross validation has comes into play. No, it's already quite a bit long back. So as you see that when you say that statistical machine learning, there's the statistical ideas, the intuitions and everything. Somebody who is more equipped with the statistical intuition and idea, they can actually apply or adapt to different machine learning methods more carefully, or they can apply that which it is more important now, because when you apply something, when you have the data, nowadays it's common tendency that we have get the data, and I have softwares, everything. There are 100 methods in the software. They just feed the data, you are going to get the output. But in machine learning, there is also one idea as garbage in, garbage out, right? If you put a garbage, you are going to get garbage as an output. But machine is going to give you an output definitely. But this intuition and the statistical ideas, those are actually will be helping you to choose what is the right method to apply. Right method to apply means which method has a minimum risk I am going to have given the data set that we are in hand, right? So this judicial thinking is very much required, and that will come to adapt or to what is called as a, like, to embrace the statistical intuition. I'm not saying that you undertake the whole lot of theories, but embracing the statistical intuition is extremely helpful. And I didn't use much of the maths, only the ideas, because it has a lot of derivations, optimization, these KKT conditions, lot of things will come up. Possibly not needed. But what the methods I am using, how much risk with that, in what situation it performs well, in what situation it does not perform well, that judicious thinking or that kind of understanding needs to be generated over the time when we are applying any machine learning methods. Otherwise, this will be difficult. It will be a disaster. Yeah, we will get some output, but we will not be having a confidence on that. So by feature selection, what we understand, I have a set of predictors and I have a response, and I am having using a linear model setup, right? That in a regression, multiple linear regression setup, what you have already learned. We may have a possible situation that you have a high dimensional scenario, means number of predictors is more than the number of rows in your data. We may have a situation, even we have a in p is less than n, means we have a regular scenario, but there is a multicollinearity among the predictors. So what means one predictor can be written as a constant of the other predictor. Not only that, those are from maths, they know it, that it may happen that one predictor can be written as a linear combination of more than two or more than two predictors. So basically, idea is that one column is a linear combination of other columns. So that is a dependent vectors. So the column space is going to be less than the number of columns in that. So in that case, the determinant becomes zero. So that comes the linear algebra concept, right? So in such a scenario, also we want to select those predictors which turns out to be more impacting to our response, important for the model. So that is something which is can be carried out either by reach, either by lasso, either by elastic net, what we have learned today. For reach, it does not have a very strong sense variable selection scenario, but whereas in lasso we do have a variable selection scenario, because a lot of outputs that are going to be exactly equal to zero, right? So there is uh, other methods also in machine learning, very pretty powerful. So I'm not sure whether those being covered here in the machine learning, when you are dealing with the regression concept in multiple linear regression. For example, it is some of the methods which is called as a best subset selection. Then you have a forward selection. These are all feature selection methods. Then you have a backward selection. Then you have a hybrid selection, right? There are different methods. So I'm not sure whether it is being covered or not. So is it being have you know these terms? Do you know this that four things I have written? No problem at all. No problem at all. I'll just have a small explanation. Then is when we're dealing with the software part, I'll show the case study. Then it will be clear to you. Okay, so I think we got one question. Mannath has asked that, sir, is there any effect of adding impurities on the output? Does it deviates the result? Okay, now what is the question is that, now let me try to understand it from this aspect, that when you are adding an impurity in an observed output, that means that means you are tampering your data itself, right? So we don't want that, right? Because data what you get directly, the random quantity, that is from the underlying process that you get, right? So usually we don't want, like, I'll give a mathematical answer for this, but first of all, let me answer from a mathematical, like from an intuition point of view, that when we are adding impurities on my response, that means it somehow talks about data manipulation, right? So we don't want to, because we plan to understand about the underlying process. So if we add impurities there, we may streamline the results the way we think. Like whatever, we may tamper with the results and everything, right? So that is not something to be done. So that's really not something to be done. And secondly, if we have a mathematical answer, in that case, when we are having a, say for example, y, if I just add up some impurities there, this does not solve the problem of the ill condition of the input matrix x that you are dealing with predictors. Its variance still going to be highly inflated, right? Is going to have a high variance. That problem is not going to solve. So in general, the idea is that we try to add some kind of impurity in which we have control, means the inputs. So if we think of an engineering system, we can little bit possibly change our inputs little bit something, so that we do. So to add with this, there are actually typically in machine learning only one setup for regression is usually covered. That your x is the input and y is an output and x is fixed. Only this much is actually in regression. All the results are everything, whatever internet you see, this talks about this only. However, there may be scenario that there is an additional error components in your response, or the inputs that you are getting, there is a measurement error in that. So when we perform this type of setup, you have a measurement error also associated with it. The regression results, then corresponding results and expressions, everything is going to change. So if you want to get little bit more idea on this, so there are different specialized book for that, but I think this is the book Casella and Barger. uh, their book, I think, statistical inference book. The name of the book is Statistical Inference. So there, I think the chapter is regression. I think there is at the end. I think the last four or last third or something. There is the regression chapter is there. There they have, you will see that they have started with least square regression. Then they have the MLE. Then they have regression on different setup they have considered. So this is statistical inference by Casella and Barger. This is, I think, one of the very foundation book. So most of the, I'm not sure, because these are some of the books, because we come from a completely mathematical background. Later we have tried to adapt the statistics and machine learning ideas. So I mainly refer which are the books I have read and got an idea of some of the ideas. So this is one of the book, so which I have read and I've got an idea from this book. So it means it is there. So it's not that somebody else has said you can find it there, something this that. No, it is not. I have read it, I have seen it, and so it is there. So you will getting the three or four ideas that when you have a measurement error also associated with your inputs or outputs, then how those expressions are going to be changed. In fact, you will get some of the very wonderful idea of regression when you have a lot of outliers and how to control over that. I think that's something related to what is something that we call it as a influence functions. So those things related to aim estimation. So those ideas also very wonderfully explained. You can definitely have it. It's a very classical book, so it's an extraordinary book.